In this video, we solve problem 115 from the Larson Calculus text, 10th edition. We're asked to choose a and b so that this piecewise function, f of x equals ax cubed on the interval from negative infinity to 2, and x squared plus b on the interval from 2 to infinity is differentiable everywhere. So first of all, one of the things that I notice is that this is just a cubic function. Multiplying by a, we'll just make it taller if a is greater than absolute value, if the absolute value of a is greater than 1. If the absolute value of a is a proper fraction between -1 and 1, it might shrink it. But that's just going to vertically stretch or shrink the graph by this factor of a. And this is just a parabola. A part of a parabola, y equals x squared, shifted up b units. We're not going to see the whole thing. We're not even going to see the vertex because we're only talking about the part of the parabola where x is greater than 2. And to get a better sense of this, I think it's helpful to graph the function and then think about sort of differentiability. So here are the two branches of our piecewise function. Because of the way Desmos allows us to specify branches, or doesn't allow us to specify piecewise functions in branches, I've called f1 the first branch of the piecewise function. So that's that cubic polynomial, but only on the interval from negative infinity to 2. And then that x squared plus b for x strictly greater than 2. Now you might notice that this says x greater than or equal to 2, meaning that the function is actually defined at x equals 2 by both branches. We actually don't want that to be true. We want this to be strictly greater than 2, but I needed to include the greater than or equal to sign so that I could plot that open circle at x equals 2, y equals 2 squared plus b. In this case, that's going to be 4 plus b in general. So one of the things I notice about this function is that it is differentiable everywhere except for x equals 2. Y equals ax cubed is differentiable all the time. I can take the derivative. I know what the derivative is just using the power rule. It's a very simple quadratic function. So the function's definitely differentiable over here. And then y equals x squared plus b, also differentiable. It has a derivative of 2x all the time. We want to choose a and b so that the function is differentiable at this point, or at x equals 2, because that's really the only place where it might not be differentiable. Now, if I want the function to be differentiable, I know that it needs to be continuous. One of the ways I can make it continuous is just by changing that value of b. Now remember what b does. If this is the y equals x squared graph, adding b to x squared is just going to shift that graph up some number of units. Well, this is just part of that parabola. I would like b to be such that this point meets this point. So I'll just increase b until we get that right there. You'd say, okay, now it's continuous. But it's still not differentiable because it looks like the slope from the left-hand side and the slope from the right-hand side of x equals 2 is not what we need it to be. We want to choose our a value and our b value so that the slope on the left, or the slope of the function as x approaches 2 on the left, is equal to the slope of the function as x approaches 2 on the right. Now you might say, is that even possible? Well, yeah. The derivative of this first branch actually depends on our variable a, and the derivative of the second branch doesn't even depend on b at all. So we know what the derivative has to be as x approaches 2 from the right, but we don't know what a would have to be so that that derivative on the left is equal, or the derivative is as x approaches 2 from the left is equal to the derivative as x approaches 2 from the right. Actually relatively simple to figure that out. We'll do that on paper, but that's our plan. We know we're just basically trying to make the slope on the left-hand side match that slope on the right-hand side. So we're going to find out what the slope is approaching as x approaches 2 from the right, and that's going to tell us what our derivative value needs to be on the other side. So f prime, in this case, can be found this way. Just take the derivative of each branch. The derivative of a constant times a cubed is that constant times 3. times x to the 1 less power. 3 minus 1 is 2. That's going to be true on the interval from negative infinity to 2. So for all x greater than, or x less than 2, excuse me. And then on the right, the derivative of x squared plus b is the derivative of x squared, which is 2, times x to the 2 minus 1, which is 1, plus the derivative of b, which is 0. That's for x greater than 2. Now, at this point, this function's not defined at x equals 2, but we want to define the function at x equals 2 so that the slope from the left-hand side and the slope from the right-hand side are the same. The slope as x approaches 2 from the left is equal to the slope as x approaches 2 from the right. So let's say, what is the slope of f as x approaches 2 from the right? So we'll just write it like that. That's going to equal the derivative of this second branch evaluated at x equals 2. Because remember, this piece defines the function for x greater than 2. Remember, that's that parabola. It was on the right-hand side of 2. So this is going to be f sub 2 of x evaluated at x equals 2. We have f sub 2 of 2. Now f sub 2 is 2 times x. So when we substitute in x equals 2, we get 2 times 2, which is 4. Sorry, there's some people with very, very loud motorcycles. I guess they really wanted to play music right now. So we've got this. We get a 4 as x approaches 2 from the right. The slope is equal to 4. If we wanted to, we could graph that tangent line at x equals 2 for this function, and we would know that the slope of the tangent line from the right is actually equal to 4. So we say, okay, we know that the slope as x approaches 2 from the right of f is equal to 4. And we also know that the slope as x approaches 2 from the left is equal to 3 times a times x squared. So we will look at that as well. So we'll have the slope of f as x approaches 2 from the left. That's going to be the derivative. I didn't put the primes there. The derivative of our first branch evaluated at x equals 2. So f prime, or f sub 1 prime of x at x equals 2. So f sub 1 prime evaluated at 2. And f sub 1 prime was this 3 times a times x squared. Well, it's 3 times a times x squared, but x is 2, so we can substitute in that 2 there. 2 squared is 4. 4 times 3 is 12. So we get 12a. So the slope from the right is 4. The slope from the left is 12a. And we want the slope from the right and the slope from the left to be equal to each other. So we're going to just set the slope from the left equal to the slope of f as x approaches 2 from the right. And so the slope from the left is this 12a. We set that equal to 4. And then we divide by 12. And we get a equals 1/3. So that tells us that our function should be ax cubed, where a equals 1/3, on the interval from negative infinity to 2 for all, so this is for all x less than or equal to 2. And then on the other side, we get x squared plus b. Now, that b does not affect, excuse me, very, very loud. That b does not affect the differentiability because the derivative of x squared plus b is just 2x plus the derivative of b, which is 0. But that b does affect continuity. We need the function to meet at x equals 2. We need the left-hand side, or the limit of the function as x approaches 2 from the left to equal the limit of the function as x approaches 2 from the right. So that's another requirement. Now we want to choose b so that the limits to meet that requirement. The limit as x approaches 2 from the left of f of x is given by the limit as x approaches 2 from the left of this 1/3 x cubed. Because we know that's the graph on the left of x equals 2. It's just that cubic graph. Well, that's continuous at x equals 2. So I would just substitute in 2. So I get 8 times 1/3, which is 8/3. And we know that that's what our limit is supposed to be. Now, I need that to be equal to the limit as x approaches 2 from the right of f of x. Now, on the right-hand side of x equals 2, our function is equal to x squared plus b. Well, that's just a parabola. That's continuous at x equals 2, so we can substitute in x equals 2. Get 2 squared plus b, so we get 4 plus b. So I need this 4 plus b to equal that 8/3. So that the limit from the left of 2 matches the limit from the right of 2. So we'll have b equals 8/3 minus 4. And 4 is itself over 1. We'll multiply by 3 over 3 to get a common denominator. This is 8/3 minus 12/3. 8 minus 12 is -4. So b has to equal -4/3 in order for that limit from the left and the limit from the right to be the same. And again, the reason why we're doing that is because we want those two pieces of the function to meet. So let's look at the graph on Desmos and see if that agrees with our handwritten calculations. My hope for you when you take this class is that you will be able to visualize these graphs when you see this function. So when you see f of x equals ax cubed when x is less than or equal to 2, and x squared plus b when x is greater than 2, I want you to imagine a cubic graph that has been stretched vertically by a factor of a, or perhaps shrunk vertically, depending on whether a is a proper fraction or a number whose absolute value is greater than 1. And I want you to see this as a parabola shifted, parabola just y equals x squared shifted up or down b units, depending on whether b is positive or negative. And we're just saying this is part of a parabola, this is part of a cubic graph. And in order to be differentiable everywhere, I need the derivative from the left of 2 to equal the derivative from the right of 2, which means everything's going to be nice and smooth. The slope is going to be the same on the left and right-hand side of 2. And I need the function to actually meet at 2. It needs to be continuous. So I need the limit of the function itself as x approaches 2 from the left, and the limit as x approaches 2 from the right to be the same value. And I need the function to be defined at x equals 2 so that our function is actually continuous and it doesn't have a removable discontinuity or anything like that. We've got b equals -4/3 ensures that the function is continuous. And if a equals 1/3, that means the slopes are going to be just right. So everything is nice and smooth. So f of x is equal to a, which is 1/3 times x cubed when x is less than or equal to 2. And x squared minus 4/3 when x is strictly greater than 2. Okay, so cool. We know that's our answer. And we can confirm our answer and make sure that our intuition and our calculations are correct using that graph on desmos.com. Okay, so it looks like when a is equal to 1, our cubic graph looks like this. To the left of 2, this is when x is less than or equal to 2. We've got a cubic that looks like this when a equals 1. And then when b is equal to 4, we've got part of a parabola that looks like this. And if you're saying to yourself, like, how do you know that that's a cubic? Well, just get rid of that restriction on x, and you'll see that whole cubic graph. That's what it looks like. But we want that restriction because that's what the problem statement said. And then this is just a parabola. I'm going to get rid of that restriction so that we can see it. That's x squared plus b, where b is equal to 4 in this case. So when x equals 0, y equals 4. Just a parabola shifted up 4 units. Again, we're only interested in the part of the parabola to the right of 2, though. So we're going to say for all x values greater than 2, strictly greater than, typically. but we're gonna write greater than or equal to so that we can plot an open circle at that point. So let's go back to b equals 1. Okay, so this is what our graph looks like. If b equals 1 and a equals 1, we have these two pieces. Now our claim was that first we needed the function to be continuous. We want the limit as x approaches 2 from the left-hand side to equal the limit as x approaches 2 from the right. Say, well, what is the limit as x approaches 2 from the left-hand side? Well, it's going to be 2 cubed, which is 8 times a. So we're going to get 8a over here. And then what's the limit as x approaches 2 from this side? We're going to have, well, 4 plus b. So we get 8a has to equal 4b. And you say, okay, well, there's two unknowns there. I'd rather not do that. So we're like, okay, let's try something else instead. So rather than looking at the limits first, let's look at the derivatives first, like we did on paper. Let's compute f sub 1 prime. But just on the interval where x is less than 2. So we see its derivative. Looks kind of like that. And f sub 2 prime. So we see that derivative. It's kind of like that. We do the calculations. We know that the derivative of this function is y equals 3 times a times x squared. So this parabola is actually a function of a. If we change the value of a, that's going to stretch the graph vertically or shrink it. Now, if we change the value of b, well, that moves this graph up and down, but it doesn't actually change the slope at all because we're just taking the y equals x squared graph and moving it up and down. So the slope stays the same, but the function value changes if we move b. But when it comes to changing a, that factor that's multiplying x cubed, the function value and the derivative itself, the derivative being the dotted line and the function being this blue line, they both change as a changes. So we said, okay, if we take the derivative of f1, or the derivative of the function as x approaches 2 from the left, and we set it equal to the derivative as x approaches 2 from the right, we found that a would have to be 1/3. If a is 1/3, then the slopes are going to be just right, so that the slope from the left and the slope from the right are the same. So I'm just going to type in 1/3 there. So if a equals 1/3, this is actually what our cubic graph looks like. And now notice, when I let a equal 1/3, the derivative graph is now continuous. The derivative on this piece is going to be 1/3 times 3, which is 1, times x squared. And then when we substitute in x equals 2, we just get, well, when x is equal to 2, x squared equals 4. So the derivative of this function is 4, our rate of change is 4 as x approaches 2 from the left now, and as x approaches 2 from the right. So this piece has a slope of 4, and this piece has a slope of 4. The problem is that they don't meet yet. They don't meet at the same location. We said, okay, well, what do we have to do to make sure that they meet? Well, now that I know that a equals 1/3, I can take the limit of this function as x approaches 2 from the left, and the limit of this function as x approaches 2 from the right. And then we can see what our b value would have to be so that the limit from the left is equal to the limit from the right. Now, because we've already chosen a, because we've calculated a by requiring that the derivative be continuous here, by requiring that our derivative have the same value at x equals 2 as we approach 2 from the left and from the right. That first branch is done. There's nothing else to change over here. This function on the interval from -∞ to 2, including 2, this is going to be 1/3 x cubed all the time. So we're not actually changing anything over there. Now, the only thing that we're going to change is our b value. We did some calculations on paper requiring that the limit as x approached 2 from the left and right were the same. We found that the limit as x approached 2 from the left was 8/3. That's by taking the limit of this. Notice that you could just plug in, if a equals 1/3, you can plug in x equals 2 here, and then you get 8/3. which is about 2.667. That's what we've got. But we also want the limit from the right to equal that. And the limit from the right is, well, it's the derivative of this, which is 2x. Or not, excuse me, it's not the derivative. The limit from the right is the limit of this function as x approaches 2. So we're going to have 2 squared plus b, so it's 4 plus b. And then we want to figure out what b is. So we subtract that 4 from both sides to get b by itself, and we found that b would have to be negative 4/3. So let's type that in for our b. And I think I want to get rid of that open circle now. And now look at it. If you zoom in, you can see it. The function is nice and smooth. The limit from the left and the limit from the right are both the same value. They're both equal to this 2.667 approximately, which is 8/3. And we can tell that the slope from the left and the slope from the right are both equal to the same value. If we were to draw the tangent line there, we would find that the slope is actually equal to 4. And we can tell that the slope is equal to 4 because the derivatives are these dotted lines. And we can tell that this derivative, the derivative of the left branch as x approaches 2, is approaching the y value of 4. And the limit as x approaches 2 from the right side is also approaching 4. So those derivatives are meeting. They're not meeting in a differentiable way. The second derivative of this function is not well defined, but we chose a and b so that this original function is nice and smooth, which means the derivative is at least continuous. And that should work. So I think that's the end of that. If we want, we could graph the tangent line there. I think I'd like to do that. Let's say y equals f(1) of 2. So it's our y value plus the slope. That's to the left of 2, excuse me, times the change in x. So I see that I draw that tangent line, and I can tell that that is tangent to the curve. It's almost indistinguishable from the curve itself. Now, if we've done everything correctly, if we use the branch on the right rather than the branch on the left, they should be equal. And they are. So perfect. The derivative from the left, or the derivative from the left and the derivative from the right are the same, and therefore the tangent lines are the same. That's a just quick way that we can check, and we can also check visually. Kind of like that problem. I guess just to finish, let's get rid of these derivative graphs. This is what we've got. We've specified a equals 1/3 and b equals negative 4/3. No, I'm not going to type it in. You could just delete this a and type 1/3 and then delete b and type negative 4/3 and make sure that you get the same graph. But I think we both know, or we all know, that if we do that, we're going to get the same graph because a is defined to be 1/3 here and b is defined to be negative 4/3 there. So I think that's a cool problem. There's another problem like that. Probably assign it as a homework problem. Very similar. We want the function to be continuous, which means the limit as we approach the points of discontinuity has to be the same as we approach those points of discontinuity from the left and from the right. And we also want the function to be differentiable. So that means the limit of the derivative on the left of some points of discontinuity has to be equal to the limit from the right as we approach some discontinuity.